introduction. And the little tidbit is that I ended up in Livermore thanks to Artie. Artie, thank you, Artie. And today, so I will be focusing on subsurface characterization, and you'll see more at the reservoir scale, based on not only seismic, electromagnetic, but also seismoelectric technique. And I will literally drive you to the path that led me to seismoelectric effects. Oops. First, a little kind of advertisement about Livermore. I know that you know us, we are almost in your garden, but I thought it would be fair to mention that we are only one of 17 DOE national laboratories. As you can see, the topics can be pretty sparse. We are what we call the multi-purpose national security lab. We were founded in 1952, so the heart of the Cold War. As of FY21, we were 8,200 employees. That number has increased since then. And that was 300 postdocs, 120 undergraduate interns, 153 graduate students. So really to tell you that we do depend on postdocs, graduate students, and undergrads. And our mission is to strengthen national security through world-class science, technology, and engineering. And again, I want to let you know that we do have undergrad and graduate student summer internship in my division, Atmospheric Earth and Energy. The application closed at the end of February, so if you're interested, first please, you can contact me, but also note the link and the references that you can follow for undergrad and graduate opportunities. Now, as you know, we are a national security lab, but that doesn't mean that we do not hire foreign nationals. And as you can hear with my accent, I used to be a foreign national myself and was hired at Livermore as a foreign national, non-US citizen. So please check the postings, and if it's not clearly stipulated US citizenship, please, you're welcome. So that was my shameless advertisement. Now the overview. Like I mentioned, I will drive you through the path that I followed to move from seismic techniques to electromagnetic techniques. And here, it's a big term, but I'm not looking at the old frequency range. We'll be focusing on ground penetrating radar. But these two aspects of techniques that can be used for subsurface characterization led me to the seismoelectric effects, which is actually the natural coupled combination of seismic and electromagnetic techniques. So more to come here. So that's a little teaser, and that tells you where we're going. So today I have three parts: seismic, electromagnetic, and seismoelectric effects to walk you through. So seismic techniques for subsurface imaging, for example, for carbon storage monitoring. And here you can see an example of Tom Talley, a neighbor from the Berkeley lab, at the post-well seismic analysis of the trivial CO2 sequestration site. That so people online can see where I'm pointing. So at that specific location, what they did is that they injected CO2 into the subsurface. This is supposed to be kind of a sealed reservoir, so that even if the CO2 moves up, and you can see here the CO2 plume, you can expect that it will stay sequestrated at these depths. But the key here is always to be able to monitor this kind of setup so that you can make sure that there are no leaking and CO2 doesn't end up at the surface, which will be something that we want to avoid. So classically, what they do to be able to image and monitor this plume is look at P-wave time-lapse anomaly. So here, just a reminder for subsurface monitoring, when you inject CO2, it's going to change the properties of your environment, so that it's going to affect, obviously, three properties. The CO2 is going to replace water, salty water, brine into the system, which is going to affect wave speed into that system. So you can use that anomaly to track the CO2. But now, on a modeling point of view, there are different ways that you can try and model that environment. And that's what I'm calling physics of the porous reservoir, which can be simple approximation, acoustic, or elastic, or if you're brave enough, look at the proelastic equations. And then in terms of the imaging techniques, you can look at, again, classically P-wave travel time anomalies, but there's more information that can be gathered if you add the S-wave travel time or amplitude, or if you go to the full waveform type of approach. So on these slides, I just want to sensibilize you on the fact that when you are a numerical modeler, again, you can choose any type of physical model that you want to characterize this subsurface. But it comes at the cost of neglecting some parameters. And if it's not in your starting equation, it's not something that you can invert for. So for example, acoustic, it's one parameter, bulk modulus, and of course density here. So looking at the compressional wave would be the kind of measurement that you'll be able to access to. Elastic, of course, you add PN and sway, and that's 3 parameters. Then you have what we call the Gassman formula. So that was back in the days and strongly used by the oil industry, a way to capture the fluid properties, but in a way which is still elastic. So you are resolving elastic wave equations, but using effective parameters which carry information on fluid and solid and porosity as, again, effective parameters, but still 3 types of parameters. And then you have the proelastic full BO type of equations and characterizations, which come with 8 types of parameters, and parameters which are directly linked to the fluid properties. And you can see that in that case, you observe not only one P wave, but also a slow BO P wave, and then your shear wave. So as you can see, complexity of physics that can be used to characterize and then ultimately to image your medium. So, a lot of equations, but it's just to show you, again, depending on the physics that you're using, you're going to have sensitivity to the parameters from that physics. Again, isotropic elastic, so that's 3 parameters, and you can see 3 types of sensitivity kernels. And here are just the expression of these kernels as part of the solid displacement, right? And I'll come back a little bit later about the adjoint approach, but that's what I wanted to convey here. For elastic, we have 8 parameters, so 8 different kernels. So as you can see, through these kernels, you can invert and get back these parameters, but you need to add them initially in the equations. So what we did back in 2011 was a synthetic case of CO2 sequestration monitoring, mimicking the 3D setup. So as you can see, that's the baseline before injection of the CO2. So if you will, that layer, the blue layer here, is just porous medium filled with saline water. And then the saline water is pushed away by that very cartoonish CO2 blob being injected in the medium. So for this simple approach, what we wanted to do is test different type of physics and see if you can recover the same type of parameters with the same resolution. And we also looked at different type of measurements, P wave travel time, but also P and S wave travel times and amplitude, and see if type of measurements was also impacting the resolution that you could recover. So as you can see here, we looked at an elastic medium, Gassman type of medium, acoustic, and fully proelastic. And these are the window picked for the P wave and the S wave. So here it's only the P wave, and that's the measurement. And here on that side, it's the P and the S. And it's a comparison of baseline, no CO2, in red, what I call the synthetic, and what I call the data is after the injection. And you can see that that has affected not only travel time, but also the amplitude. And so we are using this difference between the baseline and the CO2 injected medium to resolve the location and the properties of our CO2 and the CO2 bulb. All right. So these are the results, and sorry, it's a little small. but that's showing you the P waves, T wave speed, compressional wave speed, shear wave speed, density, bulk density, fluid density, and the fluid bulk modulus. So that's the data, what we are trying to recover. That's the acoustic rheology or physics, that's Gassman, and that's poroelastic. And as you can see, well, for the acoustic already, you can see that, yes, you get the VP, VS obviously, well, is not resolved. And for the density, same thing, a very small, if non-existent sensitivity. You can see that you have to move to the Gassman or the poroelastic rheology to really recover these parameters, not only the density, VP and VS, but also the density, the fluid density, and the fluid bulk modulus. And at the end of the day, you can tell me, well, Chris, it's nice, all nice and dandy, but you bother to go to a poroelastic rheology when the Gassman itself did a pretty good job. And that's a totally fair statement. Now, what we brought with the poroelasticity formulation is that it leads directly to these parameters, as opposed to Gassman, where you have to do some algebra to recover them. So that's the caveat.
Christina, what frequency range are you using?
Oh, that's a good point. I think the source, I didn't put that here. I think the source was at 50 Hertz. And then there was no filtering or anything. So the data itself is 50 Hertz. So it's a pretty broad signal. But what we show though is that both P and S wave travel time help constrain all the parameters. Using only the P travel time, see you don't have a sensitivity of densities at all. But no drastic differences between using travel time and amplitude. It's pretty much the same. And again, poroelastic didn't lead to any drastic improvement, but again, we get fluid properties directly. And if you also would comment on the fact that resolution is not perfect, the setup was very minimal, only 4 sources, so not a huge coverage, and that's 4 iterations. So not a big inversion and a lot of coverage involved. Nevertheless, that while we were able to resolve all these anomalies.
Maybe I missed it, but can you tell what's the change in the percentage in anomaly? Like 1% or 10%?
I had written it, but I cannot see that screen.
Yeah, me too. But so 2% change.
If I remember well, so the inclusion of CO2 created 10% increase in decrease in BP, but interestingly, 9% increase in BS, and then 2% increase in density.
So the velocity encountered 10% change.
Yes.
Okay.
Yeah, with like a CO2 or no CO2. So that's the anomaly where we are using. Yes.
The yellow location is purely CO2.
The yellow location. So, careful because I should have said that.
The water layer.
So that's
the green block.
Yeah, the green block is the CO2, poroelastic CO2. The blue is poroelastic saline. Okay, and the red is purely elastic, and the yellow here is purely elastic because they are the ceiling.
So the right panel is used to generate the data, and the left one is the initial model.
Yes. So, yes. So I'm backpropagating and I'm getting the kernels in the baseline to recover the anomaly. Okay. But again, the conclusions was that okay, we are able to do it with especially Gassman and poroelastic, but Eon and I were like very disappointed on the sensitivity to the fluid kernels, and something was missing there. And looking at what constitute these kernels, you can see that here for the elastic kernel, so you have 3 types of measurements. They're all dependent on solid displacement, forward and adjoint. So measurement of the solid ground motion. For elastic, again, we have 8 types of parameters. It's great. B and C and M are the BO coefficients. So it integrates fluid modulus, solid modulus, frame modulus. So it has all the fluid information in there. But what you can see is that to be able to construct these kernels, there are different combinations of solid displacement and fluid displacement. And you can see that the kernels which are the more sensitive and who carry the most informations are the ones that are purely solid displacement and adjoint solid displacement. All those which are across a term of solid and fluid or purely fluid have a very low sensitivity. And you're wondering, why is that? Well, it's the simple fact that seismometers are designed to measure ground motion. Nothing is there about the fluid. So the type of measurement that you're getting, and it's going to carry the information in the adjoint field, can be non-existent for the fluid displacement. You only are going to have really an adjoint solid, but you won't have an adjoint fluid element. So all these gradients are inexistent or weak. So no direct measurement on the fluid. Something is missing. We have those nice fluid kernels, but nothing really to activate them. So that was my first foray into pro-elasticity and fluid parameters. So first conclusion, comparing different models for CO2 monitoring shows the effect of physics. It is useful to model the system with the proper physics so that you can derive the parameters which are present in the physics. Pro-elastic model, like I said, they're great. You get fluid parameters directly, but at the end of the day, Gassman did an okay job.
Can you tell us what Gassman is? Because I'm not sure.
So Gassman, you still are calculating a solid saturated bulk modulus, a saturated shear, and some kind of a bulk density, but it's you use the elastic wave equation. And
it's like an effective.
It's an effective parameterization. So it still includes solid modulus, fluid modulus, frame, and porosity, but yes, in a formulation, just to get that effective parameter. So again, it's an elastic equation. Yeah. And so after the fact, when you resolve the effective modulus mathematically, you can recover, the others, but it's algebra. So the sensitivity to fluid parameters, like I said, remains weak because of the nature of seismic measurements, which are again ground motion, nothing to do with fluid. So if only we could measure more than just the solid ground motion to directly capture fluid properties, then we would be able to highlight these kernels. So that was the first layer. Missing something?
I got a question. What do you mean of solid ground motion? You mean that the receivers on the surface, we do not have any receivers in the water layer?
No, the measurement of the geophones is ground motion. It doesn't differentiate, about the solid grain or fluids. It's just a solid ground motion. So it's just the movement of
displacement.
The displacement, yes.
Okay.
You don't have the fluid displacement. Right?
Free displacement and solid displacement, both displacement, yeah.
Yeah, but the bioequations differentiate between solid displacement and fluid displacement.
Yeah.
They are two different things.
Yeah.
But the measurement of the ground motion, it's if you will, the full displacement, but mainly the ground displacement.
What's your ground displacement? Is solid one?
The solid displacement, yeah. The movement of the earth.
Okay.
Right? But what we need is something which directly conveys the fluid displacement itself. I know, right?
From the think about dynamic. It's a different equation, right? That's what.
So moving forward, again, we keep in the back of our head that it would be great to be able to directly measure the fluid properties, the fluid displacement. So on the road towards that, I did a pause and looked at electromagnetic techniques. So some know about electromagnetic equations. So these are the equations that control the electromagnetic system with Faraday's laws, Ampere-Maxwell, two constitutive equation, and the current density. That's the equivalent of the earthquake. That's the source. And that's the list of parameters: electric field, magnetic field, and electric conductivity and permittivity. And so here, if you want some association with seismic, so we're looking at modeling for the electric and the magnetic field based on a current density source. Okay, that's the equivalent. So these are the form of the equations. You can see mathematically they are curved functions, which sometimes it's a little bit cumbersome to do modeling and to integrate these mathematical formulations. So rewriting, so these are the same equations. So it does fit that there won't be too many. But these set of equations here are the same than here: Faraday and Ampere, Maxwell, constitutive, and the source. And the trick that was discovered in 2012 by Italy, I think it was working for the oil industry, was that mathematically, if you rewrite the magnetic field and the induced magnetic field here as the antisymmetric tensor, you can rewrite the equation like that. And you can see that when you write the electromagnetic wave equation into that form, that's exactly the seismic wave equation. So again, it's a nice mathematical trick. Well, it's not a trick, but it's just a mathematical equivalence. But what I liked about it is that having spent so much time implementing, for example, the BO equations in SpecFEM, I like to use SpecFEM. So I thought, hey, since it's so similar, it's very straightforward and trivial to implement this electromagnetic equation in SpecFEM. And that's exactly what I did, so that now SpecFEM can also resolve electromagnetic wave equation. As you can see, there is a convolution here for the conductivity and the permittivity. They are frequency dependent, and so that's also included in the module. So that's awesome. I've got my electromagnetic module now in SpecFEM. So that's just some example of what you can do with that. These are ground penetrating radar type of subsurface imaging, which means that you have a transmitter here. That's how they call the source in the electromagnetic world. So that's the source here. And then the receivers, there are 20 here and 20 here. And I just mimic some, a cavity here, that's the hair, what happens? And so that's just the common source gather, meaning that's the electric field in the Y direction. And you can see so the electrograms of this simple problem. And you can see that actually is the surface kind of wave, the waves it's recorded, so away from the source. And you can see that these parabola here, that's the interaction with these two cavities, and then you have more of a signal linked to all the reflections that are happening at the bottom of these little cavities and so on. These are just a snapshot of the same field at different time. As you can see, the source at the surface, propagate, interact with this void, and create all these signals. So that was, just a fun experiment. Another one that I played with is airborne GPR, which is also a quite exciting way to do subsurface monitoring. Basically, you put all your transmitter and your receiver on a drone, and then you have the drone, going at the surface and just doing, sending signal and recovering signal. So here we used it to see what's the difference that you get from airborne GPR and seismic surface survey. If you look at, so that's hair, and ice sheet here, sediment, and what if there is some melted layer at the surface of the ice? Can you see that? That's something that folks are very interested about, because glacier which sit on those melted layers can deform, and that can be of interest. So we synthetically model, so the same thing, airborne GPR on one end and the surface seismic survey on the other end. These are the properties, and looking at what's happening. These are again simple snapshots. What did I put? Two different. There must be two different electric field that I'm showing on this. Oh no, sorry. That's without that melted layer here, and that's with the melted layer here when the drone is at that position here. You can see here, there is a reflection at the surface between ice and the sediment. And here, there are some kind of reflection happening within that very thin melted layer. Same thing for the surface seismicity, without the melted layer, with the melted layer. And again, you can see also that there are some reflection at the
Can I ask quickly?
Sorry, yes.
Is the airborne GPR limited to the kind of tens of meter depth extent that your example just showed, or how deep can you apply this?
Yeah, in that case, did I put the dimension here? See, that's just what? 30 meter. Oh, that's the box is 60 here. Oh, yes, I guess that seems at 50, right? 50 meter-ish. So that would be 50 meter here from the line of the drone to the bottom of my box.
Right.
So, it's shallow, right? 50
Yeah,
meter.
yeah.
Yeah. And usually GPR is used for shallow detection.
Right.
Otherwise, it attenuates very quickly and then there's no signal. But nonetheless, you can see the difference, but still, I didn't mention that, but that's 50 megahertz for the GPR and 250 hertz for the seismic survey. So GPR2 is high frequency range. So here looking at the radiogram, no melted ice, and you can see that that's the surface because the drone is in the air, so you kind of get very nice recovery of the interface and the surface. And you can see that with the melted ice, there is some resonance happening there. Same thing for the surface seismic, no ice. Well, this is that. With melted ice, this is that too. So you really need to look at the difference between the two to highlight the signature of that melted layer. So again, just to show that EM seismic can provide complementary information on this system. So to finish with that module, I have to talk to you now about the inverse problem. So again, what was exciting, because I like a simple thing, is that you have a forward wave equation for the electric field, very similar to the seismic equation. So it was just a question of going by hand and being able to define a joint equation for that system. And like for the seismic part, it's the same equation, except for the source term, which here can be a waveform misfit or travel time misfit that we inject in the system. So same thing, we can also define electromagnetic kernels for the permittivity, the permeability, and the conductivity. And again, as you can see, strong similarities with the seismic equation. So very easy to implement in SpecFEM. So this is just to show you very quickly, because it was very close to seismic problem, I was also able to leverage seismic tools that have been that are available for full waveform inversion. For example, SeisFlows developed by Ryan Modrak. And that was very trivial to modify SeisFlows to be able to read what I call SpecFEM EM and resolve for the electromagnetic properties. And so that's a very small toy problem with two dielectric anomalies. That's the conductivity, that's the initial model, that's a true model, and that's a waveform misfit to recover the conductivity. For the permittivity, same thing, and travel time misfit actually works better with the permittivity because permittivity affects the wave speed, while conductivity, it's a dragging term, so that affects attenuation. So waveform misfit is more appropriate for that. Again, some geometry artifact here, but overall, we show that we are able to recover those anomalies. So that concludes that part for the electromagnetic. Again, I showed you mathematical equivalence between seismic and EM, which allowed to leverage SpecFEM and SeisFlows. And then I think successfully showed that we can use that module, for example, for ground penetrating radar and move it to GPR, full waveform inversion. So now in SpecFEM, we do have EM and seismic wave equations. So that's what's led to the last chapter, which is seismoelectric effect. So what are seismoelectric effects? First, let's look at the two types of settings, which are enhanced geothermal system and carbon storage. And I show you an example of carbon storage monitoring with seismic technique, right? And as you can see, we're looking at characterizing the reservoir at 1-2 kilometer depth. For geothermal, we might be looking at 5 kilometer depth, which is characterized by the circulation of water, which is going to warm up in that fracture network and then be produced back to feed those turbines and create electricity. So it's very important to be able to measure these systems, not only geothermal, because it allows to increase productivity if you know where the fracture network is situated. So, because it's not a perfect system, right? So finding systems that really link these down to top is capital. And then carbon storage, because you want to be able to detect a leakage. So seismic to electric conversion leverages these two aspects of seismic technique, which again do not capture fluid properties even when you use a photoelastic formulation, and electromagnetic technique, which are shallow but are extremely sensitive to fluid properties. So here we are looking at seismic to electric conversion, which is actually a natural phenomenon in a porous medium. So here we are leveraging both seismic and electric techniques. How does that work? So it's a pore scale phenomenon. If you have a porous medium filled with water, these are naturally charged environments. And you can see here a zoom in of a grain with cations on the part of the grain, stabilized by these anions in the porous network, so filled with fluid. And you can see that this layer, here, is what they call a bound adsorbed layer, so it doesn't move much. But then you have a full system when you get away from the surface of the grain, where these ions can be put in movement. So what happened, and that was observed in the 90s by this group, I think they were with Shell or Exxon, but they were able to model exactly that seismoelectric effect. With a seismic source, seismic wave propagates in the medium, get converted into an electromagnetic signal, especially at interfaces where it generates an electric dipole and then an electromagnetic signal. So by using this system, they were able to detect the gas-water layer in the Gulf of Texas. So that was quite exciting. And I know I'm not getting in the history of seismoelectric effect, but just so you know, it's been observed as far as the early 30s. So it's old. I mean, it's been known for a long time, but I believe that we've reached a state of HPC that allows us to potentially do a lot of interesting things with that technique. So that's just a schematic view of the type of signal that you get with the seismoelectric. If you have here a seismic source, these are collocated, and that's an important term. I'm happy to discuss more about that later on. Collocated geophones and antennas at the surface here. So you can see that's the front of your P wave, if you will. The reflection here, the dipole get created, and then electric signal get measured. And this is the mechanical or dielectric discontinuity in the medium. So in that system, at these receivers here at the surface, you can record a seismogram. And here you can see the move out of the P wave. On what we call seismoelectrogram or a radargram, what you see is a co-seismic electric signal here, propagating at the same speed as the seismic signal. Then this signal here is a quasi-instantaneous signal that happens when the front of the wave hits that discontinuity. So it creates a signal that propagates at the speed of light. So that's why it arrives at the same time. You also have, very interestingly, a third signal, which you can see appears at very early time. That's actually as soon as you do that hammer at the surface and that you generate that seismic source, there is an instantaneous electric signal that is recorded too. So you literally have a signature of the source happening in that signal. So again, on the seismic side, here you can have the reflection of the seismic signal, but you have one signal. And on the electric side, you have 3 types of signal. So, sorry, but just to, I hope, inform you that, again, what happened using Spectrum 2D and Spectrum 3D, we were able to couple the BO coelastic wave equation. And as you can see, a little bit more complex than the pure seismic wave equation, because you're solving not only for the solid displacement, but also for the fluid displacement. That is coupled with the Maxwell EM wave equations here. And what happens is that the fluid displacement, that Darcy flow here, generates a current density that can drive the electromagnetic signal. That's the seismic to electric conversion. And you also have a symmetric parameters, which is that the electric signal itself can trigger actual ground motion. That's the electric to seismic conversion. It's very unique. This one, I believe, that hasn't been observed actually, contrary to the seismic to electric. So that's what's happening in SpecFEM. We are able to do that seismoelectric calculation by coupling BO seismic equation and electromagnetic equation through that term L electrokinetic coupling, which add up to some kind of amplitude in the conversion, which is related to the charge of the system. Depending on the charge of the system, you might have a more or less strong signal. So I think that was the last equation. But going back to the carbon storage monitoring, I just designed a very simple cartoon problem, as you can see here, before CO2 injection, still mimicking that crosswell kind of monitoring. Then injection of CO2 here. So this is brine, so poroelastic with brine in the salted water in the pores. And here the brines has been removed and replaced by the CO2. And when that happened, so we talked earlier about the changes in the mechanical properties. Well, there also are some dielectric differences between CO2 and brine. And here resistivity actually, which is the reverse of the conductivity, increases when you replace the brine by CO2. So that's the anomaly that we can expect to see. So looking at that type of system, well, carried on an analysis with seismic source in that well, a series of surface receivers and borehole receivers of geophones and antennas. So here, before the injection of CO2, just kind of a sanity check and see what we can see on the snapshots. So that's here the seismic displacement, and here that's the electric field. And as you can see, the seismic displacement propagating here, so early times to here, you have that wave propagating, and you are propagating a triggered seismic electric field exactly at the same time. So that's our co-seismic signal, which was again sanity check. It's happening. It's great. After injection of CO2, we wanted to see, can we see some differences and what kind of information can be gathered from both seismic and electric. So before CO2 injection, these are the surface receivers here and the borehole receivers here. You can see that on the seismic displacement, you have your P wave here and the P wave here. So everything as expected. So we got the noise here. On the electric field, again, you have the co-seismic signal propagating at the same speed as the P wave. And then see that signal here arriving at the same time, a very nice flat curve. That's the surface. So before the injection of CO2, that's kind of what you capture, the fact that it's a free surface. And here, I know it's just a line, but trust me, the signal was there. There was the signal of the source corresponding to the exact time at which that explosion at depth was triggered. Now, after CO2 injection, you can see on the seismic displacement, P wave here, as expected. Now I know the way I'm showing it, it's like, oh, it's boring. Seismic displacement is pretty much the same. Now we know from the first part of my presentation that there is actually a slightly difference of travel time, right, between the two, because CO2 is affecting the wave speed. So if you were to actually plot them close to each other, there is a little difference in travel time. But other than that, it is just a P wave. On the electric side, you get the same signal as initially, but it's dominated by these interface signature in the electric field, which correspond to the side of the box of the CO2 here. So you can see a much richer signal that you're getting that electric conversion happening. So that the goal is to see, how to then use this type of new data set to improve subsurface characterization. So I will leave you with the fact that at the moment I'm also leading a project which is literally to practically assess the seismoelectric effects for geothermal resources monitoring, acronym C for GEO, and that's a fully integrated approach in the sense that what we're trying to see, again, is to assess that technique in terms of data acquisition, cost, and quality for geothermal imaging. And I believe that it is a low-cost technique contrary to the classical seismic and then potentially electromagnetic techniques that are done. Because for these techniques to happen, well, you need a field survey happening not at the same time. You need two different sources, a seismic source and an EM source, and then do the survey. Here, you need one survey, one seismic source, and just two types of receivers, geophones and antenna, and you get a data set which is seismic and electromagnetic. So that way it's a low-cost deployment. So we're looking at developing a C numerical package to not only look at forward, but also inversion. And in that case, we will be able to resolve seismic properties, like rock modeling, but also electromagnetic properties, resistivity, permeability, and dynamic fluid viscosity. So here is our approach where we actually get to really take advantage of these kernels for the solid displacement, for the solid properties, and for the fluid properties through the electric data set. We are also fortunate that in our team, we have a laboratory experimentalist to support and validate the numerical part, but also to inform the influence of the C coupling in the geothermal setting, because here temperature is going to have an influence. Flow of the water also might impact the type of seismoelectric signal that we measure. And the cherry on the cake is field surveys to validate the practical use of this new data set. These will be informed by laboratory experiments, but also numerical modeling. At the moment, I'm using like 2D profiles of the areas where these are going to happen, these field surveys are going to happen, and doing synthetic simulations to see how to optimally locate the receivers and make sure that we're getting a good C data set. So again, the multi-physics kind of approach, seismic and electromagnetic properties, and cost-effective since we only have one type of sources. And very quickly also what we're looking at is the frequency dependence of that coupling factor, and when we can afford to approximate it as constant, and when we do have to really fully integrate the fact that it's frequency dependent. Here you can see that's L0, so the constant term, and that's the frequency dependent one as a function of frequency. You can see that very quickly the effect of frequency is important, and that approximation, that's the real part. The approximation is not trivial. What we've shown is that at the laboratory scale, which is extremely high frequency, the frequency dependent of that parameters is very important. At the field scale, on the other end, where there is more of a diffusive mechanism, then using a constant variable actually does the job. So that was interesting. That study was interesting. Just to show you some laboratory experiments, that's what they're using. A sand layer here. They put a series of electrodes in that thing. They have a laser at the top to measure the displacement, and the source is at the bottom, and they're able to get this type of signal for the displacement and electric field. And as you can see, that's your seismic signal. So to verify that they can do that. And they're going to be working on the effect of frequency on this type of signal. And we claim that with the electroelectric data set, the seismoelectric data set, you can potentially resolve more thinner structure than with the seismic techniques. So that's something that we will prove with these experiments. But also again, the influence of temperature on the seismoelectric effect. And I think, oh yes, just one slide. We were able to piggyback on a carbon storage field deployment back in 2021. So it wasn't set up really for our purposes, but we thought that's an opportunity where we can try off-the-shelf antenna electrodes to see if we can measure the seismoelectric signal. That's a well here where they injected CO2, and they have 4 wells around that, so we can do cross-well kind of analysis. And they, where was the source? The seismic source, I think, are the stars here. And the key was to measure geophones, seismic signal, and also electric signal. So that's kind of what was resolved. We're still debating on whether that worked and whether we actually were able to capture a seismoelectric signal, but it's still a work in process. But ultimately, our goal is a field displacement this year in France in a geothermal setting. So that's a top view. That's one of the wells in which we will put our seismoelectric data instrumentation and try and measure the signal. You can see here that's the fracture network in that area, and here that's the resistivity. You can see that that's pretty complex, and we will aim at imaging and recovering that structure. For that case, we were initially looking at different type of seismic source to see what works and what doesn't work. So here there was a blast at the surface. That's our shallow well with the sea instrumentation. That's just a fault here, and how we could potentially image that fault with that system. That was here a vibroseis, so a truck kind of source. That's a microseismicity. That's the drilling here of a well. That's hydraulic injection, and that's just a power plant kind of signal. So again, we're still kind of trying to optimize what kind of source we'll be able to look at. So final conclusion, I hope that I successfully showed you that we can numerically do seismoelectric calculation. These signals are characterized by 3 types of signals. The seismic electric signal was instantaneous electric signal from the seismic source, but also very nice instantaneous signal from any interface in the system. We showed that this type of signal provide some very specific information for carbon storage monitoring and show the sensitivity to the resistivity contrast due to the injected CO2. The C dataset can capture unique information as opposed to purely seismic and purely electric. That's what we really want to convey. And that technique, again, is more cost-effective than running 2 different field survey, seismic and electromagnetic. And finally, at the moment, SpecFan doesn't have EM and the seismoelectric effects, but that's my goal, to make that open source and to integrate that with the SpecFan 2D and in the 3D. So that's my story. If you have any questions, thank you for your attention.
So we'll open this up for questions. We'll start by any student or younger generation here. Have any questions? I have some. Yes.
Hi.
Not exactly.
On the random question, to measure the seismoelectrical effects, do you use a resistivity meter system?
You know, it's a good question. At the moment, we've been using off-the-shelf electrodes. So like any kind of electrodes that you would use for ERT type of field survey. But depending on time and depending on funding, we might have to develop our own equipment to be more sensitive.
So my point is that if you use a resistivity system, it only measures the potential difference between a pair of electrodes. That doesn't give you the electrical current.
Yeah, and I don't have a slide for that, but in the lab, that's what they're using. But on the field that's Delvik, they used I don't know the term for this electrode, but that was the electric field. And we were also able to use preamp to kind of boost that signal that have been developed by a colleague in the University of New Brunswick to that effect. But that measured the electric signal. Yeah. But in the lab, you're right that what they're doing is they are measuring the volt difference, and that's creating not issues, but it's very tricky to then get to the electric field. So that's a good point. Yeah.
Okay, and yes.
My name is Parker. Really interesting talk. Thank you. To me, it seems like there's kind of a stale inconsistency almost. Like when I think of methods like ERT or GPR, we're talking generally less than 10 meters. So I'm surprised that you can see the signal at the depths you're talking about. I'm surprised it doesn't attenuate before it gets to the surface.
And that's a good question. And attenuation is a key. So the advantage of that seismic to electric conversion is that we are driving the signal at depth through the seismic signal, right? Seismic signal just keep on going. Then we know that every time we have a seismic signal, we are going to have a co-seismic signal. The interface signal will depend on the level of heterogeneities in the area. So in terms of the going deep, we'll be able to go deep. But you're right that then being able to collect a signal at the surface that is meaningful is going to be key. That's why we've been playing with preamp, and that's why we're also looking at optimizing the geometry of the field survey to be able to maximize the signal we can get. And that can be the case that we can think about field surveying sources either at the surface, but then a well to get the sensor and the electrodes kind of try and get closer to that signal. But you're right that the signal to noise ratio is our high risk kind of problem for that.
So I'd like to follow up on this, because could you quantify a little bit more in your synthetic experience, how large an anomaly can you actually see? You know, how much of a contrast do you need in that kind of geometry, realistic geometry maybe? Because if you do, for example, carbon sequestration, you're not really interested in the sequestration itself. You're interested in how much of it has leaked, right? So it's a differential, and also maybe whether you have perturbations from the leakage, right? So
it's a good point. Yeah, it's a good point. So here, and again, it's just a toy problem, and that was relatively shallow, 600 meter, and the contrast, of course, I didn't write it here, but that was a pretty close contrast between CO2 and brine that I found.
So it was a realistic kind of number, right? Okay.
And you could see the difference between the two. But to your point, and I don't have a scale here, but when you look at the seismic signal, it's your classical, nice seismic signal. For the electric signal, at some point, to be able to even verify that I was getting these three signals, I did boost the coupling parameters, so increasing the amplitude of this signal. Mm-hmm. In regular literature, and if we do actual parameters that are close to what we have, again, the amplitude is pretty small, mm-hmm. And it's all about potentially stacking all these waveforms. Use a preamp to boost that signal, and here it's just a forward calculation. But when I move to inverse approach, I think using cross correlation, stacking the signal are going to be key to be able to get measurable information.
So you're planning more like synthetic experiments with a much more complex medium?
Yes. So, for example,
just even for the forward.
Yeah, exactly. Just for the forward, mm-hmm. at that point. So here, our colleague in France have provided parameters from these areas, and they really went to town, because they know that not only do we need resistivity and permittivity information, but also poroelastic parameters for the BM equations. So they did provide parameters, with marge of whatnot. But so we do have also 2D profiles, because 3D gets expensive, but the 3D software exists. So what I'm looking at are 2D profiles in this area with 3D 3D properties, mechanical and the electric, and bringing the forward simulation in this configuration. Yeah, and see what we see.
Thank you. Any questions from the Zoom? And
That was clear, I guess.
anybody else to ask a question? Okay, well then
Can I
we'll.
ask one more question?
Yeah, sure, of course.
You know, I'm so interested in the seismoelectrical effects. Would it be possible that you are actually looking at, for example, when you strike a hammer on the ground, you are changing the induced polarization property instead of generating an electrical signal? Because you're compressing the soil, you know, that you have the electrolytes effect, the membrane electrolytes effect.
Fair enough, fair enough. But I will refer you to observation by Ivanov in 1939 or 7, and that's exactly what he did. Saturated field went by hand with his hammer, did some geophones and electrode around with his hammer, and claimed that he measured an electric signal from the conversion seismic to electric.
All right.
So there are publications to that effect.
Okay. Well, let's thank Christina once more. Whether we have pizza on the balcony.
We do, but
We
it
do?
will be a while because Laval forgot our order.
Okay, well, because it's the beginning of the semester, but it's great that if we have it, so perfect. So, I think the weather is nice.
Yeah.
But we have drinks, right?
Yep.
You need help?
That's not important.